tired of maths. I've lost count of how many times I've failed it. It's just a bunch of numbers anyway.
Hey there, budding mathematicians. I'm Exponential Emma.
I'm Radical Ruby, and welcome to another episode of
Puppet Pie, where we discuss mathematics while eating pie. On today's show, we'll be reaching out to all those people who dislike their decimals, are irritated by integers, and cringe at complex numbers, because we want to show you why maths is a whole lot more than just those values in your calculator.
We'll be exploring how math is all around us, the patterns, shapes, relationships, and all of this will be shown through a few of my favourite mathematical concepts.
And what would they be, Ruby?
Well, I will show you with a little help from our resident whiteboard. Here we have two creations of Mother Nature, the sunflower and the human arm. We've also got some human creations, such as this artwork and this ancient monument.
Believe it or not, all of these have a mathematical relationship with one another, and to show you, we'll need to take a look at a concept founded by a guy named Fibonacci.
Now, when we see these numbers, it is clear that each number in the sequence is the sum of the two previous numbers. This is the Fibonacci sequence.
But how is this useful?
Numbers are tools that help mathematicians when applying theory to contexts. So without a context, these numbers are just like having a bunch of screwdrivers lying around with no work to do.
However, if we look at these numbers in the context of geometry, we get something much more interesting.
Say we represent each number as a square with that side length. We begin with 2 squares, side length 1. The next number is 2, so we can put the square right on top. We can add each new square adjacent to the initial group. This pattern can continue infinitely. The interesting thing about this visual representation is the ratio between the two sides. The ratio of the two sides of the initial rectangle is 2/1, or just 2. Now next, with the 2 square, the ratio is 1.5. If you keep this pattern going to the 12th square, it's approximately 1.62.
Seen as though all the side lengths of the rectangles are Fibonacci numbers, we're actually finding the ratio between the consecutive numbers in the Fibonacci sequence.
Exactly. In fact, as you continue this process, the ratio continues to approach an irrational number that we like to call phi.
Ah, the infamous golden ratio.
That's the one. 1.618033.
Okay, show off. Let's just take it back to the rectangles. We can approximate a logarithmic spiral by drawing these arcs. The distance between the rotations of the spiral increase in a geometric sequence, so by a growth factor. We can link this approximate logarithmic spiral back to phi. It is an approximation of the golden spiral, where the growth factor is the golden ratio.
The golden spiral can be drawn in the same manner as the Fibonacci spiral. Instead, the initial rectangle is the golden rectangle. The ratio of the side lengths is 1 to phi, and additional rectangles added create larger golden rectangles. We draw the arcs and we get the golden spiral.
So, the Fibonacci spiral will get closer and closer to the golden spiral because the rectangles become closer and closer to the golden rectangle. Just like the ratio of the Fibonacci numbers get closer and closer to phi.
Exactly. It's all interconnected. A bunch of ratios and rectangles and relationships, more than just some numbers, I'd say. Now, back to our wonderful whiteboard. We've actually answered our original investigation.
For example, each seed of a sunflower is created after a rotation. The sunflower utilizes the highly irrational nature of the golden ratio and does an inverse phi rotation. This means the sunflower creates new seeds with no gaps, unlike the gaps that would be formed from a simple fraction rotation.
The human arm is full of golden ratio proportions. It's even shown in the fingers as well.
And Leonardo da Vinci even used the golden ratio in the Mona Lisa. Take a look. The golden rectangle aligns with the important features.
In ancient Greece, the golden ratio was utilised for beauty and aesthetics. In the Parthenon, we can see this beautiful proportion in use.
We have just explored an entire maths concept explaining things most people would think have absolutely nothing to do with this incredible science. Yes, we have used numbers, but I hope you now see the importance of patterns, shapes, and relationships when thinking mathematically. The numbers are almost insignificant. What is important is the relationship between these numbers.
What makes this number bigger than this one? Is this number the same distance away from this number as this number is? We use numbers to measure and compare, but really we're looking at what makes different ideas the same and what makes them different.
Well, that pretty much sums it up, folks. Until next time, good pie!